Okay, so why do we need integrated power management? As I said that the power management deals with the chip level. So in a single chip we have lot of regulators integrated along with lot of other modules which are mainly relevant to power management only obviously. So if you look at the power demand of a cell phone, I mean if you talk about the cell phone which we had 10 years back, uh, it was mostly the feature phone, not the smartphones, and the power requirement was less. I mean your phone used to last like 3 days once you charge, 2 to 3 days charge only once, and the battery was also not that big actually. Those batteries were like few hundreds of milliampere hour. Now we have like few thousands milliampere hours. So huge difference actually. I mean almost 10 times difference in the milliampere hour or the capacity of the battery. So the power demand is increasing because now we have a smartphones which integrates a lot of features in it. It's just like your handheld computer, because you can surf the web and you can watch videos, you can listen to music, you can play games, everything, and it has a whole processor which is used in your computers actually. So and since a lot of processing is going on and there are a lot of peripherals attached to it, like you look at a display size, it's huge compared to what we used to have earlier, and now it's a color display. So again power consumption is more, and if you look at the size of the cell phone, it more or less it's not has scaled same. If you look at the I mean same dimension, with the same proportion as your battery. So if battery capacity is increased by 10 times, that doesn't mean your phone size is also increased by 10 times. It's maybe like 2x larger than what we used to have earlier if you look at the feature phones. Not that big. So which means we have to integrate now a lot of features, and all of these features require their own power supplies. So now we have to integrate everything in a smaller space. So this means we have to deliver more power in a lesser space, and that's why we have an integrated power management where we integrate all the power supplies on a single chip, which you can see here, and the whole module is like 15 millimeter by 15 millimeter, which is 1.5 centimeter by 1.5 centimeter, and the chip size is only 6 mm by 6 mm. You can see here, and rest of the area is occupied by your passive components. So this is the advantage of integrating your regulators or power management modules on a single chip. So, and if you look at the application, so application of PMIC, when I say DC-DC converters, basically PMIC is nothing but it integrates multiple regulators on a single chip, and that's why whenever you hear about power management IC, you will know that we are talking about voltage regulators which are integrated in PMIC. So if you look at application of DC-DC converters which are mostly integrated in your PMIC or power management IC, the application, I mean almost everywhere you will find these power management IC or DC to DC converters. Your laptops, PCs, which has processor, your memory, serial links, battery chargers, everything is there in your PCs or laptops or your tablets actually. So all of these modules require power supply. Then in cell phones, there are even more modules compared to your laptops or PCs. You have processor, you have RF power amplifiers, because now you are talking about a phone, it's integrated phone and computer actually, your cell phone. Battery charger, display backlight, camera flash LED, battery management, everything is there actually. So it integrates your multimedia application, your your computer, your gaming, everything is in a cell phone. So it has lot of modules here, and all of these require power supply. So again you require a power management for this. LED lightings, which mostly requires a constant current, so we use current regulators there. So LED lighting also driven by power management. or DC to DC converters. Then energy harvesting, where we harvest the energy from environment, which could be your solar, RF, thermal or vibration, and then basically convert that thermal, vibration, RF or solar into electrical energy and power your system with that. So, all of these require again power management. Then wearables, which require have ultra low power circuits and sensors integrated on it, and they require a very efficient power management, because if you look at a battery size used here is very small, and if let us say your smartwatch battery has to last for whole day, then we cannot have a DC to DC converter which has a very poor efficiency. So, which means it is delivering a very low power, but at the same time at very high efficiency, because the battery capacity is very small and we want that battery to last for longer. So, the power management here manages everything to make sure that efficiency, high efficiency is achieved, so that your battery can last for longer. So, all these power delivery applications is mostly met by your DC to DC converters, and that is why when we talk about power management IC, we have to talk about DC to DC converters. Another application in self powered sensors, which are targeted for ultra low power applications like IoT, highly efficient miniaturized low power converters used here. Then here energy is harvested from freely available sources such as light, vibration, heat and RF. It is nothing but an application of your energy harvesting, which we just talked about in this slide, this portion actually. So, this self powered sensor are used in different applications like structural health monitoring, which is powering sensor from mechanical vibration and wireless charging. Then implantable biomedical like your pacemaker, so charging battery from heartbeat or wireless charging. So, and most of these pacemakers are, we know it, they are powered from battery. So, the life of pacemaker is determined by the battery life. So, if you can increase the life of the battery, or let us say we can recharge the battery, then you can basically increase the life of these pacemakers. So, this could be another application of power, this power management. So, health monitoring systems like wearable health monitors, where you have a multiple sensors attached to your body for different basically sensing purpose, like your ECG monitor, your blood pressure monitoring, insulin pump or breathing activity. So, this could be another application of power management. If you talk about discrete versus integrated power converters, just like we talked about Powertronics and power management IC. So, this is the main difference. On the left hand side, you can see the basically it uses separate chip for each portion of your power converter. So, obviously, the passive components like your power inductors and capacitors have to be discrete. Then your controller and power FET are also separate, and your compensation network is also external or discrete. And on the right hand side, you can see integrated one. So, you integrate these three components, which is your controller, your power FETs and compensation network, everything on a single chip. So, the only external component or off chip component will be your capacitors and inductors. So, now you can see the difference between the board size. The moment you integrate, lot of components which are used on the board will go away and will basically be integrated on this chip, and you will be using only one inductor and one or two capacitors outside. So, your board size will shrink, as well as it look much cleaner compared to your discrete solution. So, our VLSI systems or integrated systems, like I mentioned cell phone or your tablets or any other handheld devices which are powered from your battery, they used integrated DC to DC converters because we have a limited board space there. So, what is DC to DC converter? So, it converts voltage from one domain to other. As I mentioned, like if you require, your input is 5 volt, your system requires 1.2 volt, then you have to down convert that 5 volt to 1.2 volt. and then it provides regulated output voltage. When I say regulated, means it's a constant voltage across varying input voltage and output current, or varying other varying conditions such as your temperature or tolerances in the components. So, most of the systems or the chips which are used in an integrated system, they require constant voltage. So, and that is why we have a very tight spec on regulation. Most of these may not be outside plus minus 5 to 10% variation. So, if it is let us say 1 volt, then it cannot go beyond 0.9 to 1.1 volt, it should be within that range, and that is why we need a regulated output voltage. So, example is your again lithium ion battery charger. When it is fully charged, the voltage will be 4.3 to 4.5 volt, and when it is fully discharged, it will be around 3 volt. And so, your basically your output which is delivered by the battery, the output voltage is varying a lot, it is not fixed. I mean, most of the time we say 3.6 volt, but it is not exactly 3.6 volts, it is a typical voltage. But depending upon whether it is fully charged or when it is near to fully discharged, your voltage may be different. And since my system requires constant voltage, so you have to take this battery voltage and pass it through a DC to DC converter and then generate different supplies. So, if different systems will require different voltages, so most of the time we require multiple DC to DC converters to cater to different power requirements. So, these DC to DC converters could be of two types. I mean, we mainly categorize them in switching and linear regulators. So, switching regulators use inductor or capacitors or both, while LDO is basically it is a linear, so it does not require any inductor, and the LDO can generate output voltage only less or equal to input voltage, while switching regulators can generate output voltage less, greater, inverting or equal to input voltage. So, depending upon the requirement, you can decide whether to choose linear or switching regulator. So, if you talk about the differences, main differences between switching and linear regulator. So, on the left hand side, this is the basic circuit diagram, it is only the power stage shown here. So, it works on the principle of PWM modulation, where input is PWM modulator, and then based on the duty cycle of this PWM waveform, the output voltage can be varied. So, that is how we control the output voltage or regulate the output voltage when Vin is varying. So, we can say this regulation is achieved by changing on or off time here or by changing the duty cycle. Switches, these switches SP and this bottom switch which is NMOS, they are either in linear or cutoff. So, in the linear, the on resistance of these switches is kept very small. So, whenever you are charging the inductor basically or delivering the current to the load, what you turn on these switches, and what would happen, the high current will flow in these switches, and if you keep the on resistance of the switches very small, then I square R losses will be minimized. And you alternatively turn on and off these switches. So, during the on time you turn on this PMOS, and during the off time you turn on the NMOS. So, you will see a continuous current flowing into the inductor, and that is how we reduce the losses here actually. And when you are not operating these converters, you basically turn off these two switches completely, and it will go in high impedance mode. So, high efficiency is achieved over wide range of V out over V in, because your losses here if you talk about the conduction loss, it is I square R loss, it is a fixed. So, it is not depending on your voltage. So, that is why you mostly see a flat efficiency across varying V out by V in ratio. On the other hand, if we look at a linear regulator, regulation is achieved by dropping the voltage. So, if I want a let us say 1.2 volt and my input is 5 volt, then what I will do, I will drop 3.8 volt across this FET and leftover will be the V out. So, now the voltage or voltage we are dropping will cause a huge loss in this power FET, because if I am drawing a very high current, let us say 1 amp current, and I am dropping 3.8 volt here. So, I am losing 3.8 watt in the power FET. Okay. So, ultimately I am drawing 5 watt from the input, I am delivering only 1.2 watt and 3.8 watt I am losing in the power FET, because that is the only way we can regulate the output, by simply dropping the voltage. So, that is a main drawback, and that is why these switches are mostly operated in saturation, not in linear, because we are dropping a huge voltage here, and we know the, I mean, if you know the transistor theory, then VDS is large, they will be operating in mostly in saturation. So, and it has a poor efficiency when V out over V in ratio is low, which means your V out is much smaller than V in. If V out is very closer to V in, then you will achieve very high efficiency. Okay. So, the mostly the efficiency is driven by the dropout voltage, and more than 90% of power requirement is met by switching converters. Main reason is your efficiency, because I want my battery to last like 1 or 2 days. So, once you charge your cell phone, you want your battery to last for whole day at least. So, which means that will only that is only possible if you have very high efficiency, which means whatever power I am basically or current extracting from the battery, I want to utilize each and every bit of that. Okay, I do not want to lose anything. The more you lose means the battery time will reduce actually. So, so rest 10% of the power will be delivered by your linear regulator, provided that when I say unless you have a very small dropout. So, let us say you have a 1.3 volt input and 1.2 volt output. So, you will be losing only and let us say 1 amp output. So, only 100 milliwatt you are losing in that power FET. So, your efficiency here will be obviously maybe more than 90% or so. So, in that case you can use linear regulator, but we know that the moment you hook up anything directly to the battery, and battery voltage we know that it is varying from 4.5 volt like we saw here, 4.3 to 4.5 volt to 3 volt. So, and if my output requirement is 1.2 volt, then I cannot use linear regulator here, because I will lose everything in power FET. My efficiency will be very poor, maybe less than 50% or so. So, that is why we say any system which is directly powered from your battery, the 90% of the power will be delivered by switching regulator, and rest of the power will be delivered by your linear regulators. So, that overall efficiency remains very high, or system efficiency remains very high. So, here is an example. So, for V in equal to 5 volt, V out equal to 1 volt, and if let us say my load current is 1 amp. So, if I am using a switching regulator, then my efficiency will be very high, and let us say I maintain the efficiency 90% here, and obviously it will depend on how you size your power FETs. Okay. So, let us say I have sized my power FETs in such a way that at 1 volt I am getting 90% efficiency, and when I am increasing the output voltage, my I square R loss remains same, but since I am increasing the output voltage, which means, so at 1 volt I am delivering only 1 watt. Okay. In a switching regulator at 1 volt I am delivering only 1 watt, at 4 volt I will be delivering 4 watt, but my loss remains same, because I is same, R is same. So, I square R remains same. So, let us say if I have designed my switches in such a way that I get a 90% efficiency at 1 volt, then at higher voltage obviously I will get more efficiency, because now out of 4 watt I am delivering and only 100 milliwatt I am losing, and when I am at 1 volt I am delivering 1 watt and losing 100 milliwatt. So, at 4 volt I will get 97.5% efficiency. Okay. So, you can see throughout the voltage output voltage range from 1 volt to 4 volt, my efficiency is always more than 90%. Now, let us look at the linear regulator. When my output is 1 volt, I am dropping 4 volt in the that power FET. Okay. So, how much power I am losing? I am losing 4 watt. So, out of 5 watt, 4 watt is lost, 1 watt is delivered. So, your efficiency is only 20%. Okay. As I keep on increasing the voltage, output voltage, now I am reducing the dropout voltage. So, my efficiency will keep increasing. So, at 4 volt, I am losing 1 watt. So, out of 5 watt, 1 watt is lost, 4 watt is delivered. So, my efficiency is now 80%. Now, if I further increase this, so as it gets closer to V in, you will see it will hit more than 90% efficiency. So, that is why when your dropout voltage is very low, you can achieve very high efficiency from linear regulators, and we prefer to use that over switching regulators, because switching regulators require inductors and linear regulators do not require inductor. So, it is cheaper to implement and it takes lesser area also, it is more compact compared to as long as your efficiency you are achieving is more than 90%. So, depending upon this basically dropout voltage or total power you are delivering, you will decide where I want to use linear and where I want to use switching regulator. So, now another example, let us say my linear regulator is delivering only 10 milliwatt hypothetically. So, out of 1 watt, it is delivering only 10 milliwatt, which is only 1%. Okay. 99% power is delivered by your switching regulator. So, even my linear regulator, let us say achieves 20% efficiency, I do not care, because overall efficiency will not change that much. Okay. Even if it is delivering 100 milliwatt, let us say your linear regulator, still 90% power is delivered by your switching regulator. So, out of 10%, so if my linear regulator 10% power, if my linear regulator is 20% or 90%, you will still overall efficiency you will see will remain above 90%. Okay. So, this is total system efficiency which matters, and total, in order to get the total system efficiency, you need to know how much power is delivered by switching regulator and how much is being delivered by linear regulator. Okay.